Okay, so we are back with another video, as I hoped we would be. And once again this week we're doing the same sort of thing, which is to look inside something which is sometimes a bit of a black box. And I will just briefly show what the black box is. So I will start up my Python interpreter, because this is a language that has this black box built in, and I will just create a variable a, which maps from strings, which I'll call hello mapping to 1 and world mapping to 2, and I can then look up by string and get those values back. And if I put in a value that isn't there, I get an error. So this is what's called an associative array. So it associates one value that isn't natural. You know, it isn't just a number. You're not just in some sense saying, go to this part of the computer's memory and look up what's there. You're using some other piece of usually more complex data than just a number. And you're using it to look up some other piece of data. Now, Python has this built in with these dicts that I just showed. C++ has no less than two of these things called map and unordered map that do the same job in subtly but importantly different ways. But what about languages that don't have them? So I am this week not going to go to C++ because it's a bit pathological implementing something in a language that already has it, even though it's quite often done for teaching purposes. I'm going to do it in Fortran. Now, if you come from any kind of computer science background, I wouldn't bother watching the rest of this video particularly. This sort of data structure stuff is bread and butter in a computer science course, but an awful lot of people who are writing software nowadays do not have a computer science background, and this kind of data structure type stuff is a bit less common, and things like maps and dicts can sometimes look a bit like magic if you don't know what they're doing. So I shall just create my Fortran file and go from there. So I will just reload it so that my syntax highlighting works. So I will say, first of all, the key thing is what I want to do in Fortran is to just have, say, an array. If I have an array of 100 elements, which I call data, I can then do data of 7 is 16, data of 28 is 4, and I can then print those back. And I get the numbers that I put in back. So long as I am trying to look up just based on a number key, then it's really easy, because I can effectively say, okay, go to the start of this data array in memory, jump forward this many elements, and read the data that's there. And I can just immediately get that data. So how do you generalize that to working with non-numeric things? And the answer is there's lots of ways, but the simplest answer, and one that Python uses, and one of the ones that C++ uses, is what's called a hash table. And the idea there is you just find some kind of algorithm that takes your more complicated, more general key, a string is what I'm going to be working with in this case, and just turns it into a number. And then you can look it up in an array. Now, if you're still listening and you are from a computer science background, you will see that I'm missing an important element of how these things actually work in reality, and I will come back to that at the end. But just for simplicity at the moment, we will ignore that. Now, I will just show how this works. Can't spell. So I'm going to create a function. I call that hash mod just for simplicity. Use iso fortran env going to put in implicit none. Okay, so my function is going to be called hash, and it's going to take a string for my key, and it's going to take a number of elements. I'm going to call it NE. Now I will say I'm not really using anything particularly Fortran specific in this. If you were in another language, you could implement this exactly the same basic way so long as you have arrays available to you. There are a few differences in the details, but that's all. So that tells me that my key is a string and that my number of elements is an integer. And my return type is going to be an integer, 64-bit integer, because of the fact that I want to be able to have potentially quite a lot of elements. I'm only going to use a 100-element array, but we are going to pretend that potentially we might want many more. So what I'm going to implement here is one particular hashing algorithm. There are a lot of them. This is one called DJB2 by a man called Daniel Julius Bernstein, who is, I believe, based in the University of Illinois at Chicago. And it's called DJB2, and it's not a particularly sophisticated algorithm, and it has some things in that are or look like magic, and because I'm not really going to be going into this here, I won't even try and explain it, and it's not really my area either, but we'll just put the magic in and you will see that it's magic, and you can try other values because you'll be able to see where the magic goes in. So the first thing I'm going to do, I don't need a separate NB in this implementation. So I'm going to set my return value initially to be 5381. Now that is very definitely the big part of the magic. That value is actually important, and picking different ones makes this hashing algorithm work less well, and we will come later to what I mean by less well. Okay, I'm now just going to have an integer array variable here because I'm going to loop over my string. So I'm going to loop over all the characters in the key, and I'm then going to say that the hash value becomes the modulo division, or the remainder of the modulo function of, and I'm going to do ishift, which is a Fortran function that returns a value of a variable but with all the bits shifted. So this is working with the number at its low-level bit type representation, and I'm going to take my existing hash value and I'm going to shift all of the bits in it round by 5. So literally all of the ones and zeros that make up my current hash value, I'm going to shift them round by 5 bits. So effectively that would multiplying the number by 2 to the 5, which is 32, I believe. Okay, so I've done that. I am then going to add to that Okay, so IHR is something that returns me an integer representing the ASCII character value for a given character, and I'm going to take the current character of the key that I'm working with. So this is just taking the letter and turning it into its ASCII value representation. ASCII, if that's something you're not familiar with, is just one way of converting from a printable human-readable character to a number. Computers really only work in numbers, so the only way you can represent letters is by having a number that represents a letter, and then when it's drawn on screen, it looks up what letter to draw in response to that number. Okay, this outer int here is used because I want to convert that to a 64-bit integer because I'm using 64-bit integers. And I then take the modulo of that, or the modulo division of that, with the number of elements. Okay. And then at the end, because I'm using Fortran and my array that I'm going to look up in it doesn't start at 0, I'm just going to add 1. Now, I don't believe that adding 1 affects the performance of the hash at all. I'm almost certain it can't, but sometimes these sort of things can be a little bit on the unnecessarily clever side. So you have to be a bit careful. But this should work and work well. And that's basically it. So what I have is a function that takes in a string and will return a number based on that string. So let's just have a look. So I'm first of all just going to print the results of it. First of all, I shall use my module. And I'm then going to do hash of, let's say, hello. I'll do hello and world. That's what I did before. Okay, so I compile that, and I missed a bracket. Where did I miss a bracket? 5, double close. Ah, yes, I missed an element here. After I've done the shift of the hash, I have to add it to itself. Now that is the other magic number. As I say, this I shift hash comma 5 plus hash is just a sophisticated way of multiplying by 33. And it's a fast way of multiplying by 33. I probably shouldn't have done that, but if you actually look up DJB, this is the implementation that you will see. So yes, I just missed something, because I am working off notes for this video. You can't derive this. And this 33 here is another magic number. This 5381 is a magic number. This 33 is a magic number. They are there for very good reasons, and they do work well. And there are people on the internet who explain why. And I forgot my end function. There we go. Yes, and I have to say this, so I have to give it a number of elements. So now we're actually ready to go. So I compile this, and I get 70 and 78. And that's deterministic. Every time I run it on the same inputs, I get the same outputs. And that is important, of course. So I now can not just print those. What I could do is I could do data of that equals 16. And then I could do that is 24, and let's do one more. Say hello there. That's 99. So I now print that back. Now it is worth pointing out this is case sensitive, of course, because the ASCII values for upper and lower case letters are different. You can make it non-case sensitive by basically making everything uppercase when you calculate the hash, and that is the way it's usually worked. Okay, so we get out 16, 16, and 99. So yes, I put in hello twice, that's why. Because this one should have been world. Okay, we get out the right numbers, 16, 24, and 99. So I have now reproduced effectively what I had in Python. I can look up a number from a string. And this right-hand side, I'm using integers here, but it really could be any type because I've just got an array of them. Now, this is where the complexities come in. So first of all, what would happen if I put in 101 of these elements? The answer is this hash function is set so that it is guaranteed it will produce a value between 1 and 100. So as soon as you have 100 elements, and realistically, almost certainly way before you have 100 elements, 2 of those things will generate the same hash value. In this version that I've implemented here, once you hit that repeated hash value, you will overwrite the previous data, and it will be gone. That is not how things work in Python. That is not how things work in C++. And that's because in a real version of these hash tables, there is another step. You don't just have this array here of the data. What you have is instead an array of arrays. So for every hash value here, you inside it have, well, 2 arrays effectively, one of the key and one of the value. And as soon as you calculate the hash, you go straight to the bucket, as it's generally called, and you then look through all of the keys inside that bucket until you find the key that matches and read out the matching value. And that means that you now don't have to worry about 2 things hashing to the same value because you're eventually comparing on the exact key. So you only get that collision if the keys are the same, and the keys being the same, that is what you want. If you try and store 2 values under the same key, you want to replace the original value with the new value when you do the second store to that key, because the key is supposed to be unique. But at this point, you can immediately see that there is a problem. Because what happens if you have not this hashing function, DJB2 hashing function that works well? What about if I had an absolutely terrible hashing function which always returned 1 or always returned 26, say? Doesn't matter. Always returned any valid value. Well, at the moment, with this version I've actually implemented, you would only ever be able to store 1 value, 1 key, 1 value. But with the buckets, you'd be able to store as many as you like. But what would happen is you would always go to exactly the same bucket and linearly look through your lists of keys and values. And that doesn't sound like it's very good, because if you were willing to do that kind of just looking up in a list, why not just do that from the start? And there's a reason why you don't want to do that. So I'm going to go here to the C++ reference website for the unordered map, which is in C++ usually implemented as one of these hash tables. I don't believe it is strictly required to be. It gives other requirements, but it doesn't require it actually be a hash table. A hash table is just the simplest thing that works like it. And here is a key point. In it working properly, search, insertion, and removal of elements have an average constant time complexity. So in a sense, that's what we've got here in this version when it's working well. For any given key, you go away, you look up, you work out the hash. The time it takes to work out the hash actually depends on the length of the key here, but we'll ignore that. But once you've got the index into this array, it takes exactly as long to look up the first element as the 99th element, barring a few minor questions about memory accesses. But essentially, every element takes the same length of time. So this is why you have this constant time complexity. But it's only true on average because of the fact that you get these collisions, and at some point you have to look through your list of all keys that are in a given bucket. And so that's sort of the strength and weakness of this. If your hashing algorithm is working well, so that you don't have lots of key value pairs stored in a given bucket, then this is extremely efficient. You can look up an element instantly, exactly the same as you can look it up in just a normal array. Hash tables are very efficient. so long as your hashing function here is working well and you don't get a lot of collisions. So that basically requires both a good hashing function and also that you have enough values here, enough buckets, that you don't force things to start going into the same bucket simply because you've run out. Yeah, so don't run out of buckets. That, to a degree, is it. All that you really are doing is you're coming up with a function that turns your key into an index in an array. There is then this complication of buckets, where within the array you have to do a linear lookup to find the exact key that matches the key that you're searching for, which I haven't shown here. But that's not difficult. And these things are very efficient. They're classic data structures going back a long way in computer science history. And there is still very active research into what makes a good hash function to make the thing have the properties you like. And this is one of the reasons why C++ has two of these associative containers. So unordered map, which as I say is pretty much think of it as one of these hash tables, has an average complexity of order 1. So it doesn't matter how many elements are in there, it takes the same time to look up or to store an element. And a worst case scenario of order n. So if there's a lot of collisions, a lot of things in the same bucket, then the time it takes to do that linear search through depends on the number of elements. Now, I'm sure somebody clever will mention you could order the elements within each bucket and then do a binary bisection, which would get that down to an order log n worst case scenario. And you can, but only at the cost of increasing the effort involved in insertion in absolute time, even if you improve it in complexity. So the difficulty is in getting these hash algorithms to work well. So the other thing that C++ does, the standard map rather than the unordered map, uses a different type of container which always, on average, will take log of the number of elements in there to do a lookup in it. But it has the advantage that all you have to be able to do is order the items, because it's based, in practice anyway, it's based on a tree-based system. So rather than having to come up with this hash that goes straight from this is my value to this is my storage location, it merely requires you to be able to say, is it bigger than or smaller than this one? Bigger than, smaller than. And you just at each time answer bigger than or not. I think it's actually less than that you have to implement in C++ to make that work. But that's basically it. Associative arrays, they are really useful. In languages that have them, like Python and C++, definitely use the built-in ones. They're not especially easy or fun to implement or debug, although they can actually be an interesting project if you look at them as a project rather than a working part of a piece of software. But you can implement them yourselves if you're working in C or Fortran, and there are plenty of libraries that do them as well. But as I say, the point of this video is to try and open up that black box a little, and we should be back again next week with another video.